Okay, we're back after example 2. As promised, we're going to look at how we deal practically with the temperature effects. There are two choices. The first one is to use a self-compensating gauge. So the strain gauge and backing self-compensate for temperature-induced strain. This type is more expensive, less common. The other option, and the option that we would be using in lab, if we were doing lab, but will be demoed for you, would be to use a compensating dummy gauge. In this, the compensating dummy gauge sees no strain. So you place this on something that's going to be the same temperature as what you're trying to measure the strain of, but it doesn't see that strain. And the effect is that those temperature effects on on the resistance from the active and the compensating gauges cancel in a bridge circuit. So that's just the big picture. We have slides that it's going to explain that in more detail. So let's do that. Here we have a Wheatstonebridge, which you should be familiar with by now. And we have two strain gauges. We have RG1 and RG2. R3 and R4, those are just fixed resistances that are equal to the unstrained resistances of RG1 and RG2. So if we meet all of that and we place RG2 on what we want to measure the strain of, and then we place RG1 on something that isn't subject to any strain, but subject to the same temperature, then these two, or the effects on the resistance in this Wheatstonebridge will cancel out. So the output voltage will not change. It's a tricky way of dealing with all those temperature changes. One other thing too, you want to have leads that are roughly the same length. The resistances of different leads might affect your measurement too. Okay, so here, how will we measure the strain gauge resistance? This is just going to be incorporating what we just looked at. We're just going to learn some different variants of it and the names of these. So first, we'll also drive the equations for what the output of these should be based on the strain and the gauge factor and all that. So if we have that same configuration that we just talked about, where we have one active gauge and one compensating dummy gauge, then we would call it a quarter bridge. So it's one active strain gauge, quarter bridge. Now, if we started out with well, actually, before we even start, I was going to say when we start out with the Wheatstonebridge equation, which would be this, but what we need to back up even further for is to define what RG2 and RG1 are. So RG2, so it's just that equation for the effects of strain and temperature. Note here, a lot of these U's are supposed to be subscripts, but they jump up, and there are other letters later on too, I believe, other than just the U's. I don't know, Microsoft Office will not cooperate with me. I've changed that many times, and it just keeps popping back to this. So I just tell you that I kind of gave up on trying to get those to all work. I don't know if I just have too many of them on this slide or what, but don't get confused by some of them being subscripts and some of them not. There is no U in this. So we have the unstrained resistance, the effects of strain, the effects of temperature. And then down here for RG1, which is the dummy gauge, we have all that, but it's not experiencing any strain. So we drop that out of it. And since we learned that these two will cancel each other out, so the temperature effects have no effect on the output, we can just drop those terms from it too. So RG2 and RG1 become these. And then these are what we substitute in to the Wheatstonebridge equation. So here we're still just starting out with RG2, RG1 plus RG2, and then RU plus RU plus RU, right? R3 and R4 are RUs. So if we do that, and then we substitute these in for RG2 and RG1, and we take the 2 out here, we simplify it down to this. And then we can further simplify it down to this, right? This cancels out one of these. And then it looks like I got hit a little ahead of myself. This is the point here where we substitute these in for RG1 and RG2. So here we're substituting these in for what we simplified this down to be. And we simplify that, we get to this. This just brings that up from the previous page. And then, so here we can have this, we can simplify this denominator more. For small elastic strains, the 2 times the unstrained resistance is going to be much greater than the effects of the strain. So we can drop that out, we come to this and we simplify it down to this. So the output voltage is going to be equal to the source voltage times the gauge factor times the strain. So we'd probably be arranging all of this to solve for that divided by 4. Now, there are some interesting things here. So remember, this is one active gauge, it's a quarter bridge, and our sensitivity is a quarter of the gauge factor. It's this S divided by 4. Like we said, the compensating gauge must be placed on an unstrained piece of the same material at the same temperature, and leads should be the same length. We already said all that. And this is a really important thing. For the quarter bridge, the half bridge, and the full bridge, we'll learn about the half bridge and the full bridge, you must meet these initial conditions of it being balanced to begin with if you want to use these shortcuts. So like it says here, unless the following is true, so unless R3 and R4, those fixed resistors, equal the unstrained resistance of RG1 and the unstrained resistance of RG2, if those don't all equal RU before those are strained, then you cannot use this equation. Say if these are all 350, but this one's 500, then you can't start with this. You would need to start back with this. And you wouldn't have, these wouldn't be RUs, they would be R3s and R4s. So R3, R4, and R4. So make sure that you have that balanced initial condition if you're going to use any of these shortcuts for the quarter bridge, half bridge, or full bridge. Now we're moving on to the full bridge. I'll give you a little hint that as part of your homework, you're going to need to derive, like what's done in these slides, for the half bridge. So we're skipping over the half bridge now, we're going to the full bridge. You're going to have to do the half bridge on your own. But in the full bridge, we have 4 active gauges, and 2 are in compression and 2 are in tension. So imagine this like it's a cantilever beam. You have 2 of the gauges on top and 2 of them on the underside. So when you apply a load out at the end, that end goes down. The 2 in top will be in tension and the 2 in the bottom will be in compression. All these are active gauges. So RG1 and RG4, these would be 2 of them that are in, since it's a positive sign, these would be the 2 that are in tension. And since this is a negative sign, RG2 and RG3 would be the two that are in compression. We have the unstrained resistance. We're including the effects of the gauge, sorry, the strain, and the effects of the temperature. Just pointing out that sign change. We start with the full Wheatstonebridge equation. This one, the S isn't behaving and being a subscript like it should. So RG1 is equal to RG4, and RG3 is equal to RG2. So if we make those substitutions in, we can simplify this down to this. And then I believe this is the point where we substitute in these for RG2 and RG4. Yep, so we get to that. And here we can simplify this down. Like, so this and this will cancel each other out. These add to get that 2. This cancels that out. In the denominator, this plus this equals that. This and this cancel out. And this plus this equals that. So we still have these temperature effects in here. Before that other one, we knew that they canceled out, so we said that they canceled out. In this one, though, we want to do something like we did in the denominator, where we say the unstrained resistance times 2 is going to be much greater than double the effects of the temperature. So we can get rid of this. So temperature effects will cancel out. So if we then take that and we simplify it down, we would get to this. Right? So this goes away, the 2 and the 2 disappear, the RU and the RU disappear. So we just have source voltage, gauge factor, strain. It's that. So that's the equation for the full bridge. You have to have nominal or unstrained resistances that are equal for all 4 for that to be useful, or for you to be able to use that. And the sign indicates polarity based on setup of bridge. You can flip that just by switching leads. So it's 4 times the sensitivity of the quarter bridge. We don't have that 4 in the denominator. That's it for this. I think we'll stop here, and we will pick this up with the load cell and the displacement cell soon.